Our project aims to maintain the user's finger mobility while rehabbing an A2 finger pulley injury. Pulley injuries are common in rock climbing as they occur when the tensile load applied to the pulley is greater than the ligament's max allowable force. Two members in our group are climbers, so there was a personal motivation to interview a need knower with this injury and explore mechanisms that could reduce and rehab injury during activity. Our need knower is a mid-20s experienced climber who appears to have strained or torn his A2 pulley. After injury, he stopped climbing to allow for recovery, but he seeks an affordable low-profile solution that allows him to continue climbing. We wanted to develop a device that rehabs pulley injuries while reducing pain and being affordable, so we're not restricted to climbing specific needs. Relieving load on the pulley reduces pain and allows the pulley to heal over time. Two common recovery methods are circular taping and thermoplastic rings. Taping is affordable, but it restricts circulation, plus its biomechanical effectiveness is minimal and likely doesn't relieve enough force on the pulley to prevent further rupture. Rings help restore range of motion, but are obstructive when completing dexterous tasks.
Here is a diagram for external pulley device. On either side of the injured A2 pulley are two rings. A string passes through both of the rings and wraps around a friction drive, which is directly connected to a ratchet and pawl mechanism. At the end of the string is a rubber band, which removes the slack in the string. A torsional spring is connected to the pawl and keeps the pawl engaged with the one-way ratcheting gear when it's in its default position. The pawl is also connected to our servo motor, which has two states, default and disengaged. The PCB board sits behind the servo motor and contains a Raspberry Pi Pico and a 5-volt voltage regulator, along with the wiring. The system is mounted to a standard wrist guard. As seen in this video, when the pawl is disengaged, the finger can freely flex and extend. When the pawl is engaged, the finger can freely flex, but any load experienced from the finger is applied directly to the external pulley device, not the injured finger. A load test with a target load capacity roughly equals the weight of a half gallon of milk and a safety factor of 1.42 was conducted. The device ultimately passed the test as it was able to support 2.7 kilograms without the displacement of the finger exceeding 1 centimeter from the original position.
To control our device, we use MicroPython running aboard a Raspberry Pi Pico. Our software tracks two states for the ratchet, engaged and disengaged, both referring to the pawl's position. When the user grasps an object, the pawl is engaged to place all weight on the external pulley. To allow free motion, the pawl disengages when the user releases the weight to reopen their hand. The EMG sensor we use to decide when to disengage is imperfect, so a push-button listening for interrupt acts as a manual override. This is crucial since a user's hand should not be stuck in an extension position if the sensor fails. We also had to account for false positives. The most common case is when the user already has their hand open and makes any sort of motion that falsely triggers the EMG. We ensure a waiting period between each disengage action. We also program the pawl to auto re-engage shortly after disengaging so that the user can continue lifting other objects if desired. In this video, you can see when the user wants to release the ratchet and move their finger freely, perhaps to let go of an object or pick one up, an EMG sensor placed on the posterior forearm triggers the servo motor, which is connected to the pawl via a short string to rotate counterclockwise and pull the paw from the engaged position with the ratchet gear.